Hi Applied students, this is Miss Glenn. Today I'm going to be talking to you about the central limit theorem that we've just learned about in class. So I want you to think about the applet, the one with the three graphs. The gray graph at the top and that blue graph that we were studying. Think about that applet for a second. What we were learning and what we were discovering is that if you take a population, that gray graph at the top, doesn't matter what the shape of that population looks like, but if you take a population and you sample from that population, and the thing that you sample is you take a bunch of data points and you record the mean, what you end up with, that blue graph, is called the sampling distribution of means. So what we're referring to is, think about the applet, the sampling distribution of means, that is the third graph from that applet. What I do is I take data from my population, however many I've decided as my n value, 2, 5, 10, for example. I record that number of data points from the population, and then I calculate the mean of those data points. That is that blue block that dropped down into the third graph. So theoretically, to get that blue graph, what we do is we repeat that sampling process an infinite number of times. Now in our example, we first animated it by doing one sample. Then we maybe clicked the 5 button. Then we clicked the 10,000 button or the 100,000 button. So we didn't quite get infinite, but we got a very large number of samples. And with each sample, we collected, let's say, n equals 10 data points, and we recorded that mean. So now we have, let's say, 100,000 means recorded, and that's what makes the blue graph. So the thing that we were recording, in this case, was the mean of each sample. And that's what makes this third graph. And what we noticed about that blue third graph is that it was approximately normal shaped. Approximately, it wasn't always perfect, but it was approximately normal shaped if we had done enough samples. At 5, it probably wasn't great, but by 10,000, it looked much better. We also found that if you looked at the gray graph's data and at the blue graph's data, both had the same mean. The blue graph itself has a special way that you refer to its mean. So here's what I know. On the population, the way we refer to the mean is mu, and we learned about that in class already. In general, let me leave myself a little side note. For a sample mean gets its own special symbol, and that's x bar. So to talk about the mean of means, what I mean by that is the center of that blue graph, or the mean of that blue graph. What we use to describe that is a kind of a combination of these two symbols, mu and x bar. We say mu sub x bar. That's the mean of means, or the center of that blue graph. And given enough trials, what we notice is that that mean of means, or the mean of the blue graph, was approximately equal to the mean of the gray graph. Another thing that we discovered when looking at that applet is the difference between the gray population spread and the blue sampling distributions of means spread. So if you remember on the applet, you had the gray graph up here at the top. Ooh, that is a really large pen size that I don't want to use. You had the gray grid graph up here at the top that maybe looked like this if we're talking about the normal population. And then there was the middle graph and then the blue graph down below. Our blue sampling distribution of means graph maybe looked something more like that. And even if we switched and we're talking about, a skewed population, our spread of our population was much wider than the spread of the sampling distribution of means. So this sampling distribution of means, this third graph, has a much narrower spread than the population. So the fact that it's got a narrower population means that things like, well, the spread itself or that range are going to be smaller values. But what that also means is if I'm thinking about the way that standard deviation works, that tells us about the clustering around the center. So for example, if I was looking at this one, standard deviations are going to be kind of large because of the way that that spread goes. A standard deviation that's this distance away, well, that's the whole graph for my sampling distribution of means. So I better not have the same standard deviation that is sigma in this case. On my sampling distribution of means, I'm going to need to have much smaller standard deviations. In order to find that distance, we use a formula. It's smaller, and the statisticians and mathematicians have noticed over time that that standard deviation can be calculated as sigma divided by the square root of n. So what we're doing is we're taking, let's use a new color. We're taking the population standard deviation and we're dividing it by the square root of n, where n is the number of data points in your sample. So what that was, n in our applet situation, was how many gray points dropped down onto that second graph. It's the sample size, the number of data points that were in that sample. And now with all of that information, I can now actually make the specific normal curve that I'm going to use to describe the sampling distribution of means, given any information about a specific population. So for example, let's pretend I knew that I had a population where the population mean, remember this is mu, that's our population mean. Pop mean was 82. This is our population standard deviation of 17 and an n value, which is our sample size, of 20. With that information, I can now draw, remember this normal curve is going to be my blue third graph. I'm drawing the sampling distribution of means here. I'm drawing this one in essence. And I don't actually get to see the population, I'm just given the stats about the population. So what I learned from the applet was that the blue graph, this third blue graph, was centered at the same place that the mean of my population was centered. So the center of this graph should match. It should also be 82. Technically, because it's on the third graph, this one is now mu sub x bar, the mean of means, but it should also just be that value of 82. Then, in order to put all of the other standard deviation markings on this normal curve like we should, and of course this is just an estimate of where those lines are, I need to figure out what I should add as far as what is one standard deviation that I should be adding or subtracting from that mean to find those next values on the x-axis. So to find those values, I need to know what the sampling distribution of means standard deviation is, which we refer to as the standard deviation of means. So in order to find the standard deviation of means, I'm going to use the equation that was provided to me. Sigma divided by square root of n, where I know sigma and I know n because those were provided to me right here. So sigma we know is 17. N we know is 20, and now this is a value that I can plug into a calculator and figure out an answer for. So let's do that. In my calculator, 17 divided by square root 20, and I get 3.8013 blah blah blah. So I'm going to round to 2 decimal places and call this 3.80. So that is my standard deviation. So on my normal curve that is my sampling distribution of means, that's the standard deviation that I'm going to add or subtract to get at each of these standard deviation marks. So I'm going to take 82 and I'm going to add 3.8. And that gets me 85.8. And then I'm going to do that again. I'm going to add 3.8. And that gets me 89.6. And then I'm going to do that one more time. And I will get 93.4. Then going the other direction, from my mean of 82, my mean of means, I'm going to subtract the standard deviation 3.8. So I'm going to say 82 minus 3.8. And I'm going to get, oh, I need to get rid of that arrow so I have space. I'm going to get 78.2. And I'm going to subtract 3.8 again. And I get 74.4. I'm going to do it one more time, subtract 3.8. And I get 70.6. And now I've successfully made the normal curve that represents the sampling distribution of means. And normal curves are really helpful because they have that 68, 95, 99.7% rule. So if you remember, oh, I don't remember which colors we used in class, but we have 68% of our sampling data exists within here. 95% of my sampling data, or of sample means, exists between 74.4 and 89.6. And then 99.7% of my sample means exists between 70.6 and 93.4. So when we get to problems later on that ask about the context, we'll need to use that 68, 95, 99.7% rule. And there you go.